Here's what I'm going to challenge you to do as we get going with our combustion notes here. Make your own set. See what yours would look like before looking at mine. So we had our reactants and our products, the atoms that we started with, and then the atoms and molecules that we finished with. So reactant things I'll try to do green, products yellow, and then combustion. So combustion, we made our little fire, and that was with our alcohol that started in our little dish here. And alcohol produced this cool fire, this flame. And as it burned, the level of the alcohol went down. And we had our alcohol as our fuel source and oxygen going into it. Those are the two reactants that we need. And that produced our two products, which were carbon dioxide, that non-flammable gas, and water, which condensed on the walls. So alcohol, the type I used is called isopropyl. It's C3H7OH. And then oxygen is O2. So what do those look like? Alcohol has 3 carbons and then an OH group right in the middle. And that is going into the flame. That's what the reactant means, that it's going into the flame. And the oxygen also is going into the flame. So those two things going into the flame is going to recombine all of the carbon, oxygen, and hydrogen into our new molecules of carbon dioxide. That's CO2 and H2O. And we see our carbon dioxide is coming out of the flame and our H2O, water, is coming out of the flame. Those things are products. And we say that those things are reacting, or they're reacting to forming. And what that means is the atoms are smashing into each other and rearranging to make those products. Now, if we balance this, I'm not going to go over how to balance right now. Great topic, but save that for another day. You need 2 alcohols, 9 oxygen, and 6 carbon dioxides, and 8 waters in order for this to happen. And there's 2 ways to think about that. That is the least number of molecules of each that you need, or it's the mole ratio. For today, I'm going to think about it in terms of that's the least number of molecules you need for this reaction to take place. So it's not just 1 alcohol coming out, it is 2 alcohols. That's part of the recipe for this reaction to take place. So 2 alcohols go from the liquid, and then they're going to react to form. They're going to smash into 9 oxygens. And when they smash into these 9 oxygens, all the atoms from the alcohol and those oxygens, they're going to rearrange and become carbon dioxide. And you'll get 6 carbon dioxide molecules from that smashing together. And they come out, and when they're all hot, they're floating up at the top of the jar there. And then you have 8 waters that come out. And these waters come out in the gas phase, but then they condense on the walls into that liquid phase. So they come out as that real hot steam gas, and then they condense on the walls. And I'll get those. I forgot some of the bonds there. I'll get those in just a second. And so our carbon here, if we count them up, we have 6 of them that we start with from the alcohol. So 6 carbon from the water, 6 carbon from the alcohols. And then our hydrogens, if we count them up, hydrogen again is only in the alcohols. So how many do we see? I left one off. We have, count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 15, 16. There's the one on the oxygen there. The 16 hydrogens from our alcohols. Now, oxygen, there's oxygen in both molecules. There's 2 in the alcohols, and then there was 18 in those 9 oxygen molecules. So we can show that here, that we had, let me change that 6 to a 3 here. Made a little boo-boo. So that's 6. We had 3 carbons in each one of our alcohols, and we had 2 alcohols that made our total of 6 carbons, right? We had 8 hydrogens in each one of our alcohols, and we had 2 alcohols that made our 16 hydrogens. And then in terms of oxygen, we had 2 oxygens in each one of our, 1 oxygen in each one of our alcohols. Let me change that there. And we had 2 alcohols. So that's 2 oxygen from those. And then we had 2 oxygen in 9 different oxygen O2 molecules. So we get 2 oxygens from the alcohol and 18 of them from that O2 gas. And that combined to make our 20 oxygens. Now those atoms are what are rearranging to make our carbon dioxide and water. So carbon, all of the carbon from the alcohol goes into that carbon dioxide in complete combustion. And we're just thinking about complete combustion here. If you've heard of incomplete combustion, we'll save that for another day also. So there's 1 carbon in each CO2, and there were 6 CO2s. And hydrogens, if we count those up, right, we have 2 of them in 8 different waters. So that is going to be 16. So 2 of them in 8 waters. And then oxygen, again, the oxygen is split up between the 2. We have some oxygen that are in the carbon dioxide and some that are in the waters. And that's our 20 total that we have there when we counted them all up. So in carbon dioxide, there's 2 oxygens in each. And we had 6 of them, so that would be 12 that we'll get from the CO2. And then we have 1 oxygen in each of those waters, and there's 8 of those waters. So that is 12 plus 8 gets us 20. So we see all the atoms that we start with, we also end with. And this is the least number of molecules with those atoms needed for this reaction to take place. And all of those carbons came from the alcohol. So all of our carbon dioxide carbons come from the alcohol, and all of the hydrogens for the water came from the alcohol. And I just feel like that's so cool. Chemistry and physics, a lot of these things just, it almost seems like magic, but it's just so cool. It's fun to be able to explain it, but somehow it's just cooler than the explanation even warrants as we learn about it. So let's zoom in on this intersection here of the alcohol and the air and think about vapor pressure. So vapor pressure here, we have are cold. If we think about the alcohol being cold versus when it's hot. So we sometimes tried to light the alcohol and it hadn't been lit yet, so it was cold. And then other times it had been burning and it was hot. So those are our 2 little scenarios that I have going on here. So when the alcohol is cold, the molecules are going into the gas phase, but less of them are. So less are banging into those walls, exerting pressure on the walls. So there's fewer gas molecules, and they're also moving slowly. So colder things move a little slower, and we'll get into more of that later, another day. And the hot alcohol, they're coming out. We have more alcohols banging into the walls of our container here. And they're also moving faster. So more molecules also moving faster. That would increase our vapor pressure. So more molecules moving faster. So what did this do to our lighting? So in terms of combustion, in order for something to burn, you need about 16% oxygen, and air has about 21% oxygen. So there's enough oxygen. Now in a liquid, there's very low concentrations of that oxygen down in the alcohol. That's why it doesn't burn in the alcohol, but there's plenty of oxygen in the air. So we got to get that alcohol into the vapor in order for it to burn. And the more vapor we have mixed with the oxygen, the more combustion, more fire we can get. So there's plenty of oxygen above the alcohol, but not nearly enough down in the alcohol for combustion to take place in the liquid. So our cold one lit really slow because we had to warm it up in order for it to get moving faster, more molecules. Whereas the hot one, it lit really fast. And again, it lit slow because there's few gas molecules moving slowly, and that was contributing to our low vapor pressure. And this one had to warm up for the reaction to start. So lower vapor pressure, harder for our alcohol to light. Whereas when we had our higher vapor pressure, it was a lot easier to light. That was when, you get it within a ½ inch there and it lights. So our gaseous alcohol slows or limits the reaction rate. So our gaseous alcohol slows or limits the reaction rate. So we need lots of that gaseous alcohol because there's plenty of oxygen inside the air. Now, when we think about the mass of the oxygen, we talked about it sinking versus floating. Oxygen has a molar mass of 32 grams per mole. And I won't go over how to do that right now, but each oxygen has a molar mass of 16 grams per mole, and there's 2 of them. Whereas carbon dioxide, molar mass is 44 grams per mole. So you add together the two oxygens and the carbon, and that is 44 grams per mole. So the carbon dioxide should have been the one that sank, whereas the oxygen should have been the one that floated. But we saw some different results. So our small mass should lead to floating. Our big mass of carbon dioxide should lead to sinking. But the oxygen gas in the air hadn't been really warmed. It was colder, whereas the CO2 coming out of the fire, it had just come out of the fire, so it's hot. So what does that do that allowed the CO2 to float, whereas the O2 sank? Because the CO2 had come out of the fire and was hot, it's going to be less dense. It's more spread out. And that is going to allow it to float there. Whereas the oxygen gas, even though it's less massive, it's going to be more dense because it's cold. And so that will lead to it sinking in this situation. Conservation of energy is really cool. And I feel like it's the harder one to kind of wrap your mind around, but hopefully we can get it here. Let's look at the energy stored in each one of the bonds in our molecules. So carbon and hydrogen store 416 kilojoules per mole in each one of those bonds. Carbon and oxygen, they store 336 kilojoules per mole in each one of their bonds. And carbon-carbon store 356 kilojoules per mole in each one of their bonds, and oxygen-hydrogen store 467 kilojoules per mole in each one of their bonds. Oxygen-oxygen hold 498 kilojoules per mole, and carbon-oxygen hold, they're a bigger one, 1,073 kilojoules per mole, and oxygen-hydrogen hold 467 kilojoules per mole. So here's how we can connect that. When bonds break, energy must be absorbed. Okay, so all the reactants bonds are breaking. When bonds form, energy is released, and that's our products. They're forming new bonds. So if we think about the number of bonds that there are, and we'll do some calculations here. So in terms of carbon-hydrogen, like how many carbon-hydrogen bonds did we have that had those 416 kilojoules per mole? So carbon-hydrogen, there's 416 kilojoules per mole. And how many times did we have that? Well, if we count them up, we had 14 of them. And we could say, okay, there's 7 in each molecule. We had 2 molecules. That's 14 total. So that's going to be the amount of energy that's stored in carbon-hydrogen bonds. Now let's think about that carbon-oxygen bond right there. Okay, there's 356 kilojoules per mole. That's just our energy unit, kilojoules per mole. So there's 336 kilojoules per mole. There's one molecule that we have, one in each molecule that we have 2 times. And so that's 2 molecules. Now, 2 bonds. In the carbon-carbon, now we have 356 kilojoules per mole. How many of those bonds do we have in each one of our alcohols? There's 2 of them in each alcohol. And then we have 2 of those molecules for 4 of them total. So we'll multiply that number by 4. Now, oxygen-hydrogen, how many oxygen-hydrogen bonds do we have in each one? Well, there's 467 kilojoules per mole, and there's 1 oxygen-hydrogen in each molecule of alcohol, and we have 2 alcohols. So we'll multiply that one by 2. So these ones that we have here that I just wrote down the numbers for, that is for our alcohol, our isopropyl alcohol. And that's how we'd calculate all the energy in those bonds in that isopropyl alcohol. So what about the oxygen? The oxygen had that oxygen-oxygen bond, that's 498 kilojoules per mole. And how many of those bonds do we have in each oxygen? Well, it's not per, you see there's 2 bonds there, but that's 498 for that double bond, that double covalent bond. Okay, so there's 1 of them, and we have 9 oxygens, so that's 9 double bonded oxygens. So once we say how much energy went into breaking all of those bonds, because all of them have to break in order to reform in the products. When we add those numbers together, as long as I plugged them in right and wrote down the right ones, we get 1,336 kilojoules per mole. Okay, 1,336 kilojoules per mole. That's energy that's going in to breaking this, to breaking apart our alcohol and oxygen. But they don't just stay broken apart. The reactants, have to reform into our products. So let's look at our number of bonds, their total, and then we'll look at our types of bonds that we have. This one's a lot simpler because we really only have two different types of bonds. So we have our carbon-oxygen bonds here, and carbon and oxygen. What's the amount of energy in each one of theirs? Well, 1,073 kilojoules per mole. You have two of those bonds in each one of our carbon dioxides. And so if you count up how many carbon dioxides we have, there's 6. So that's 12 of those bonds total. So we'll multiply 1073 by 12. And then if we look at water, that's an oxygen-hydrogen bond. And that oxygen-hydrogen bond, how much energy does it store? Well, 467 kilojoules per mole. And you have two of those in each one of our waters. And how many waters do we got? We got 8 that come out of the fire. So that's 16 of those types of bonds total. So now, how much energy is released when all of these bonds form? Let's tally that all up here. Again, so our top one was our CO2. Our bottom one there was our oxygen. And this is going to be our energy output. So let's times 1073 by 12 and 467 by 16, and hopefully got all the right numbers here. So this is our energy released, our energy output, and that's for our bonds to form. And we get 20,384 kilojoules per mole. So we see a lot of energy comes out here. And right now it looks like more energy came out than was present originally. So let's think about what happens here. Because we have all this energy release, the change in energy for our little system here is the energy in minus the energy out. So the change in energy is going to be the amount of energy stored originally, which was that 13,336, and then subtracting that 20,384. And we get negative 7,048, and that's the energy that's leaving. So negative 7,048, that's the amount of energy that's leaving our system as that fire. So a classic exothermic graph is your reactants start high and then products go to lower energy. Endothermic is you have lower energy ending at higher energy. So for us here, our energy left, so it's leaving. So the reactants have higher energy and the products have lower energy. And so we had an exothermic reaction. Combustion is exothermic. And so the last way I just want to show how to hopefully clarify this here, what's going on when we break those bonds. So when we're putting in energy, that's our bonds breaking. It took 13,336 kilojoules per mole to break those bonds that we saw in our alcohol and oxygen. So that's the energy that's put in for our reactants. And then how much energy was given off, right? We had almost 20,000 kilojoules that are given off there, right? So that's our 13,336. That's the energy going in. Now we got all this energy that's given off here that we have to account for. So here's our energy output, and this is from our bonds forming. When our bonds form, this is going on in the products. And we had 20,000, a little over 20,000 kilojoules per mole that get released. So since we had all this energy get released, that means we have all this cool extra energy. So we have this 20,384 that gets released, and that leaves us with this extra energy. So where did that extra energy go? So that energy doesn't just disappear because we don't create or destroy energy. It gets released. That 7,048 kilojoules per mole, it's released as that heat energy. That's that flame that we see right there, which is really cool. And that's what's going on. That's what makes the fire. So the energy stored in our reactants and our products. I hope you enjoyed doing combustion with me, and I hope you got our takeaways that you need two things in order to do combustion. You need a fuel source and oxygen, and then you produce three things, well, two things with atoms. You produce your carbon dioxide gas, you produce your H2O water, and then that energy is released. And then I also hope you got our main takeaways that the atoms in your reactants rearrange into your products, that the carbon, hydrogen, and oxygen rearrange from the alcohol and oxygen into CO2 gas and H2O water. So the same atoms become new molecules. And then also I hope you get that the energy didn't magically appear, that we got the energy from those bonds being broken and reforming in the reactants and products. Hey, if you like that, subscribe, and I'll see you next time. FlemDog Science with me, Caleb Fleming. Subscribe, like, comment, and hit that bell.